Hello, you're welcome. All right, so the topic before us is static electricity, okay? Or you can also refer to it as electrostatics. So, what is static electricity? Now, static electricity is the type of electricity that is generated by static charges. Static charges. So, what's a static charge? A static charge is actually charge at rest. Charge at rest. That means the charge is immobile. So, of course, electricity generally is divided into two types. Okay, so one form of electricity is the one that we are learning, all right, which of course is static electricity, static. While the other form of electricity, which we are going to learn, which we are going to study later, is current electricity. So, the difference is for static electricity, the charge is at rest. So electricity of charge at rest is static electricity. Then, of course, current electricity deals with mobile charges. Okay, so please take note of the difference. All right, so now the question is static charge. What is the origin of a charge? Okay, or electric charge. Let's just discuss the old origin of electric charges. Okay, so electric charges actually originate from matter. Remember, every matter is made up of atoms, and atoms have electrons and, of course, protons. So anytime any material loses electron, it becomes negatively charged, so it acquires a negative charge. Please pardon me. Anytime any material, okay, if a material loses electron, remember electron generally is negatively charged. So what's going to happen to that material? Because it loses electron, then the net charge on that material becomes positive. So anytime a material loses electron, it becomes positively charged. Now, on the other way around, if another material receives that electron, all right, then it becomes negatively charged. So charge is actually is a particle, of course, which is electron. So the number of charge, the amount of charge that you have, depend on the amount of electron that is found in that particular material. So invariably, charge, okay, quantity of charge can be calculated as the number of electron then multiplied by electronic charge. One electronic charge is equal to 1.6 times 10 raised to the power of minus 19 coulombs. Okay, and of course you know that the charge of an electron is also equal to the charge of a proton, but that's just by the way. So invariably, so we use this to calculate the quantity of charge. So by the time you multiply the number of electrons by the charge of one electron, that will give you the total quantity of charge. So as we already know, there are two types of charges. Electric charge will have the positive, then of course we'll have the negative. Okay, all right, so now let's look at how uh, these charges are being produced. Now, electric charges can be produced either through friction, basically through friction, or number two, by induction. Okay, so let's look at the production of electric charge. So through friction or by induction. Or number 3, or it can be by contact. So let's explain them one after the other. Now, by friction, you are rubbing a material on another material. For example, okay, let's look at a typical example. When you actually rub an ebonite rod on a 4 material, okay, you just rub this, let's say an ebonite rod on 4, or you rub a glass rod on 6. That's any cloth material. So just rub glass on cloth. Okay, so glass rod on a silk material. Now this is actually friction, rubbing one material on another material. In the case of ebonite rod, what will happen is this: the 4 will lose electron, will release electron, and that electron will actually come into the ebonite rod, thereby causing the ebonite rod to be negatively charged. So the ebonite rod will gain the electron from the 4 and becomes negatively charged. But in this case of glass rod with silk, in this case, rather, it is the glass rod that will lose electron, and of course, the silk actually collects the electron. So the glass rod becomes, by the time you test the charge of the glass rod, you discover that the glass rod is positively charged. Ebonite rod is negatively charged. So please take note of that. All right. Now, in the case of induction, by induction, you are not bringing that particular, the 2 materials together, but rather you are bringing it close to each other. So let's say this is a sphere that I want to charge by induction. So I can bring a rod that is already charged. Now let's say I want to make, if I want to produce a positive charge on this sphere, then I'm going to bring a negatively charged rod. Okay, I'm going to bring a negatively charged rod close to the sphere. Now what is going to happen? The negative charge of the rod or of this material, it may not necessarily be a rod, will repel the negative charge. Remember, like charges, we're going to talk about that in fundamental law of electrostatics. Like charges repel or like charges attract. So the electron, which of course has a negative charge, will be repelled to the other side. Okay, so because I'm bringing a negative charge close, so all the electron goes to the other side, leaving a net positive charge at the end where the rod is actually, okay, where the rod is brought near to. Then the question now, because now I have one side of this sphere is having a positive charge, the other side is having a negative charge. Now, how do I get rid of the negative charge so that this negative charge at this other side, so that I will now have this sphere completely having a positive charge? That is the point where I will now have to apply what is X. Okay, connect the rod to X. Okay, so once I connect the rod to X, then the excess negative charge that is actually found here passes through the connection and of course enters into the earth. So the result is that this sphere now is all positively charged. So that is the result I have. So this is by induction. Okay, then the case of contact, you're actually bringing that particular material in contact with the material that you want to charge, and they will have the same charge. So look at what is going on here. Okay, in the case of charging a sphere, all right, by induction, any charge you want to produce on this sphere, you're going to bring the opposite charge close to it. Like in this case, now I wanted to produce a positive charge, then the rod or the material I'm bringing close to the sphere is a negative charge. So a situation where I want to produce a negative charge out of the sphere or out of any material by induction, then I will have to bring a positive charge close to it. So that is charging by induction. All right. Okay. So the fundamental law of electrostatics we know. Okay, actually state that like charges repel each other, repels, while unlike charges attracts. So, of course, this is one law. Okay, but it's one law, and it's the fundamental law. There are other laws, but the fundamental law is what we have here. Like charges repel. So that simply means that if I bring a positive charge close to a positive charge, the force that will exist between these two charges is that of repulsion, so they will repel each other. But if I should, on the other way around, bring a positive charge close to a negative charge, then you can see that there's going to be a force. The force that will exist between these two charges is the force of attraction. Okay, so that's going to be the force of attraction. So these two we attract. Unlike attract, unlike charges attract, while like charge actually repel. All right, so I hope that is well understood. Now let's look at another law of electrostatics. So this law is known as the inverse square law. Of course, is Coulomb's law. According to Coulomb's law, the force of attraction or repulsion between two charges that is separated by a distance. Okay, let's say we have two charges of quantity q1, another charge q2 separated by a distance r. According to Coulomb's law, the force of attraction or repulsion between these two charges is directly proportional to the product of the charge, that is q1 times q2, and inversely proportional to the square of the distance apart. The distance between the two charges q1 and q2 is r. Q2 is r, so that's r square. You know, in mathematics, we always replace the proportional sign with an equal to. Then we have to introduce a constant. So F is equal to K Q1 Q2 all over R square. So now, the force, of course, is electric force. The F is the electric force. The K is the electric force constant. It's a constant. Okay. And of course, if we make it subject of the formula from here, if we make K the subject, I'm going to have F R square, then divided by Q1 Q2. So that way now, the SI units, the SI unit of K is going to be SI unit of force, which is Newton, then SI unit of distance, square, meter square, then SI unit of coulomb times coulomb, that is per coulomb square. That is the SI unit of the constant K. So the constant K is given, the SI unit is Nm square per coulomb square. Okay, so please take note of that. So now, since it's a constant, does it have any constant value? Yes, it has a constant value. The constant value, okay, according to coulombs, is 9.0 times 10 raised to the power of 9. So anytime you're being given a question, okay, to calculate electric force between two charges, the value you're going to use for K is approximately 9.0 times 10 raised to the power 9 Newton meter square, and of course per coulomb square. Now, how did he arrive at this particular constant? What formula actually gave us this constant? This constant is gotten from this formula, 1 all over 4 pi epsilon 0, 1 all over 4 pi epsilon 0, okay? 4 pi. So it is the combination of all the constants here that actually gave rise to this, okay? You can actually prove that yourself. You know what what the value of pi is. Pi, of course, is 22 all over 7. Pi is a constant 22 all over 7. Then epsilon, this symbol epsilon 0, is what is referred to as the permittivity. Permittivity of free space. So since we know very well that the two charges, in this case, okay, we are taking the two charges to be in a free space. That means the space that is around the free charge is a free space of simply A. Okay, so permittivity of free space. That is what epsilon 0 represents. And it is approximately the constant value is 8.85. The permittivity of free space, 8.85 times 10 raised to the power of minus 12. Okay, and of course, we can also derive the SI unit for it. That's the SI unit for permittivity of free space is going to be the opposite of the SI unit of this, okay? Or the inverse, not the opposite, the inverse of this. So that's going to be per Newton per meter square, then coulomb square. That is, okay? So permittivity of free space is per Newton per meter, then of course coulomb square. So by the time you fix in these values into this, you will discover that K is equal to 9.0 times 10 raised to the power 9 Newton meter square per coulomb square approximately. So you can actually try that yourself to prove that K is that value. All right. Okay. So here we go. Now let's illustrate this with an example. So simply, let's say you are being given two charges. Q1 is 2 microcoulombs. Okay. Q2 is 3 microcoulombs, and the distance between the two charges is let's say 30 cm. So you have to calculate the electric force. Okay, so solution. So here we go. We apply the formula KQ1 Q2 all over R square. So first, K is 9.0 times 10 raised to the power of 9. Q1 is 2 microcoulombs. To convert microcoulombs to coulombs, you have to multiply by minus 6. Remember, micro is always times 10 raised to the power minus 6. So 2 microcoulombs, that's 2 times 10 raised to the power minus 6. And of course, for 3 microcoulombs, I'll have the same times 10 raised to the power minus 6. Then divided by the distance. The distance is 30 cm. I have to convert this to meter. cm to meter, that's 30 all over 100, that's 0.3. So that's going to be, okay, 0.3 square. So F now is going to be equal to, okay, so now this is standard form in this course, all right, electricity and magnetism. Your calculation, your numericals will deal with, you're going to deal with a lot of standard forms, so you should know how to work with standard forms. So now let me give you a simple method of working with standard forms. So you can actually ignore the powers of 10, then work on your other integers, of course, or real numbers. Okay, later you now bring the powers of 10. So what I'm going to do here is I will multiply 9 times 2, which is 18, then times 3. Of course, that should be, let me get a calculator. So as I said, I deal with the numbers. 9 times 2 times 3, of course, that's 54. Then divided by 0.3 squared, that should give me 0.09 if I'm not mistaken. Yes, that should be 0.09. Okay, so divided by 0.09, 600. So this is 600. Okay, so I have dealt with all this, so I'm left with the powers of 10. So how do I work on the powers of 10? That's times 10 raised to power 9. Of course, this is indices, you have to just add the powers. Okay, 9 minus 6 minus 6. So at the end of the day, I'm having 600 times, this is going to be 10 raised to power minus 3. And you know very well, 600 times 10 raised to power minus 3 is the same as 600 times 1 all over 1000. Reciprocal, and you end up having 0.6 Newton. Okay, so I hope that is well understood. All right, so this is just an introduction. There's a lot we're going to do, okay, but I'm going to stop this video for now. We'll continue in the next video. So see you in the next video. Thank you very much.